Okay. Anybody can help? Yeah. What?
It's there would be the probability for flavor is given to be theta.
Mm-hmm.
There would be four variables: RC, GC, where the red cherry and the green cherry would be the wrapper, and red lime and green lime would be the wrapper. So red cherry will have RC vectors. So we'll be multiplying for red cherry it would be theta into 1 minus theta 1 when for the cherry case, and similarly we'll just multiply all these multiply this will be the.
That's basically the point. I mean, so what he was saying is that so this is just kind of skips a couple of steps, but it's not that many steps. Let me just see if I can show this. Yeah. Where are we? 44 and 45, right? This one. Yeah. So this is a is a combined version of. So there are n examples, right? N data examples. For each data example that you have seen, you can compute its likelihood. Okay. The most important thing is that all the data examples, I mean, those of you who spend any time reading any of the learning literature would see this thing which just sort of skip over, IID. Okay. Identical and independently distributed. Independent and identically distributed. So each one of the examples are independent of the others. So if you see two examples, if you see the probability of seeing the first example is P1 and the probability of seeing the second example is P2, then the probability of seeing both is P1 times P2 because they're independent. Now to compute P1 and P2, you use the same exact distribution, the distribution that is shown by that particular Bayes network. Okay, so this is, if I actually just had, let's say, one red and one green, okay, then the flavor red, so suppose I got, let's see, yeah, so we basically can have, there's a flavor and the flavor being cherry versus flavor being lime, and the wrapper being red versus wrapper being green. Right, those are the two things, right? So suppose I have my example E1 is a cherry in green wrapper. The probability that such an example occurs given this particular network is what? It's theta for the cherry times, if it was a cherry, the probability that you would use a green wrapper, right? This is the probability. If it's a cherry, the probability that you would use a red wrapper is theta 1. Okay, green wrapper would be 1 minus theta 1 because it's one of those two. Okay, so this would, for this particular example, it will be theta times 1 minus theta 1. For the second example, E2, let's say it is a lime with red wrapper. Okay, then the lime part is going to get you 1 minus theta because notice that you picked a lime and then you decided what wrapper to put it in. So the prior probability that you have a lime is 1 minus theta because this is the probability of cherry, 1 minus that is the probability of lime. Okay, so 1 minus theta times red wrapper given lime. You get red wrapper given lime with theta 2 probability. Okay, so now what do you have? You have theta times 1 minus theta 1 for the first example, 1 minus theta times theta 2 for the second example. Okay, so if you multiply the whole thing, you have theta times 1 minus theta times theta, no, theta times 1 minus theta times theta 1 minus theta times 1 minus theta 1 times theta 2. Okay, and as more and more examples come, okay, this would have, you'll get more and more thetas for every red, every cherry candy you see, you have to multiply by a theta. So theta would be ultimately multiplied C times, where C is the number of cherry candies. And then 1 minus theta would be multiplied by L times, where L is the number of limes. Right? Okay, and then 1 minus theta 1 would be, and 1 minus, and then the other 4 will come in. Okay, 1 minus theta 1 would be green wrappered cherries. Green wrappered cherries. Okay, so that is the number of green wrappered cherries you find. Every time you find a green wrappered cherry, you have to throw in a 1 minus theta 1. Right? So I did all this and I just basically wrote, one single expression. That's all. Those are the steps that are missing. Is that clear now?
Yeah, that's right.
Is that clear? Okay. So that part is basically what, so you basically computed the likelihood for every one of the data points, given the hypothesis, given the distribution. Right? And now, since all data points are independent, you can then multiply all these probabilities. You will then get the probability of the whole data, which is the multiplication of the probability of individual data points. Okay, and then the whole point of MLE is that you are saying, given two hypotheses, two distributions, which both could have generated this data, and I'm asking you which distribution do you think is the right one, you are assuming that the distribution that gives higher likelihood to the data that you actually watched is the one that must have generated it. Do you see what I'm saying? The distribution that gives higher likelihood to the data you saw is the one that has generated it. Okay, so that basically would then mean that since this is the expression for the likelihood of if you ever watched N candies and you found L of them are limes, C of them are cherries, and RC of them are red wrappered cherries, GC of them are green wrappered cherries, RL of them are red wrappered limes, and GL of them are green wrappered limes. So much, of course, so that, of course, RC plus GC is equal to C and RL plus GL equal to L. Right, that's the point. Okay, this is what you just observed. So then you could have then computed the likelihood of seeing all that data given this particular distribution as that expression. Now the interesting thing, of course, is you only figured out currently this distribution has variables. It has the topology set, but it did not quite make up its mind as to what should be the parameters, the CPT parameters. Okay, so all you're doing now is to say that I can deal with that by basically, I should set these parameters to those values that will make this expression maximum. Right? Okay, for different values of theta, theta 1, theta 2, you get different numbers here. So if you plot this in this, what dimensional curve are we talking about right now? What dimensional surface are we talking about right now? So this is a function, right? This is a three-dimensional function. It's actually 3 dimensions. Yeah, so it's actually 4-dimensional function, right? Because there's a function has a value for every 3-dimensional point. You can't quite see it. It's already out of your camp. Okay, so there are 3 dimensions. For every 3-dimensional vector, there is a number the function gives to that, and that is this. That number comes out here. So you're trying to, and it's a continuous function. It's giving values to each one of these points, theta, theta 1, theta 2, of course, over the simplex. Right? So then the question is, for which specific values of the theta, theta1, theta2 is this function taking the highest value? That is where the calculus comes in. That is where you are trying to compute the max of this function with respect to the variables that are, that you have access to, theta, theta1, theta2. And to do that, you then take the partial derivatives, equate them to 0. Okay. I mean, of course, there is also this question that, as you know, just taking the partial derivatives and equating them to 0 is not enough to compute the max. You also have to do the second derivative test. In fact, in the case of multivariable functions, you really have to do the second derivative is a Hessian, right? I mean, if you have n variables, you have n square second derivatives, right? And then you take the determinant of this function. Do any of you remember this stuff? How many of you have done calculus 3 in school? Okay, so go back and look at it. It's all there. Okay, no, but I mean, the reason is this. I find, I'm in sort of the same boat as you are in. I was in the same boat as you are in, maybe worse, because I actually knew continuous math and used continuous math forever when I did my bachelor's in electrical engineering. Okay, and then one day I decided that I am a computer science guy, and so I could forget all my calculus. Okay, never touch calculus again. So if you're an electrical engineering major, like the first day you go in, you'll start using calculus that you learned in the high school. If you're a computer science major, the first day you go in, you get to forget all your calculus until you take machine learning, because suddenly you start using calculus there again. Okay. So it will come back. If you have learned it once, it'll come back. And one of the other things to understand is that it's nice to know that there is you can get stuck in all this minutiae of different algorithms, and understanding that all they're doing is a slightly different way of finding the maximum of the function. And they're all basically about gradient ascent or gradient descent. Okay. In fact, I want to show you this. This is Newton-Raphson method. This you should know, right? Okay. Newton-Raphson method is basically how to find the zeros of a function, right? Newton basically came up with this thing to find. You may have seen this, in the context of finding square roots iteratively, for example. Okay. And the idea is that to find the zeros of the function, what all Newton basically said is you can start at any point in the function. I mean, in fact, one of the other funny things is if I show you the function, you know where its zeros are. Right? It looks like a silly thing to do. Okay? What I'm giving you is the function in analytical form. And then you're trying to find where its zeros are. And that is basically root finding. Okay, for arbitrary nonlinear equations, finding roots is not easy at all. Okay, so what Newton basically said is that, I mean, this should be repetition, for most of you, that start anywhere on the function. Okay, let's say start, take some value. So you're finding root basically means this is a two-dimensional function. It's actually a two-dimensional function. That means for each value of x, there's a value of y. And you're trying to find the 0. Here is a 0 because at this point y value is 0. You want to know the x value for that. That's all, right? So what we're saying is start from any x value. Okay, start from here, let's say. Then you know what its y value is. Okay. Now at this point, I want to somehow move towards the 0. And the idea that Newton had is consider the derivative there. The derivative is the slope of the tangent at that point. Right? Okay? So here is the tangent, the blue line. Now I take the actual value of the derivative there. Right? And that will give me the slope of the tangent. Now given the slope of the tangent and also the fact that the tangent is going through this, I know the equation of the line. And furthermore, I can figure out where this line hits x-axis. All Newton essentially said is where this line hits the x-axis is a better approximation for your x. That's it. Okay? So you now say this is my x value. And you take the y value here. If it is close enough to 0, you say I'm done, I'm going home. If not, take one more derivative and then find the slope again and see where it hits and say that is the x. This is one of the most simple, calculus ideas. And it's kind of interesting to note that if you could do this for multidimensional functions, then most of machine learning is just a footnote. Okay? Because most of machine learning winds up optimizing, some continuous function. In statistical machine learning, we're optimizing in this particular case, we're optimizing the likelihood function. Okay? So the question is just find the optimum. Now, finding the optimum is connected to finding zeros. Why? Because you take the derivative and find its zeros. Right? Finding the zeros of the derivative will give you the maximums. Right? So maximum finding is connected to zero finding. The only difference is if I'm now finding if this function was my f dash, then what Newton would say is take xn plus 1, the next iteration x value to be the current iteration x value minus f dash by f double dash. The original Newton thing would actually look like this: xn plus 1 equal to xn minus fxn by f dash xn. That's what you would have seen. Now, since what I'm actually finding zeros of is f dash, wherever f is occurring, I put f dash, and wherever f dash is occurring, I put in f double dash. In one dimension, single variable calculus, this is so easy. Okay, but when you get to multivariable calculus, this f double dash is essentially a matrix. Right? Because, so if you have just two variables, then you have dou f by dou x square, dou f by dou y square, dou f by dou x dou y, dou f by dou x dou y. Right? Oh, the opposite way? No, what you're looking, your face. What? No, I'm writing this. So what did you say?
I think should one of those be the y and the dou x?
What?
Should one of those be y and x?
Oh, dou x, dou y, dou x. Yeah, that's true. I mean, I should write it that way, but it's the same, right? That's one of the points. Actually, so what he's saying is, I'm assuming that what you're saying is, you write this as dou x, dou y, and you write this as dou y, dou x, right? Okay, fine. Okay, but the point is that there are n squared second derivatives. If there are n variables, if there are n variables, there are n first derivatives and there are n squared second derivatives. And it turns out that and in fact you can do Newton-Raphson in multidimensional for multidimensional functions, but then every step winds up having to compute the Hessian and basically taking the denominator. And most people don't want to do that. Most algorithms try not to do that. You see what I'm saying? Most algorithms try not to do it. Okay? And to avoid doing it, basically so that the per step complexity is reduced, they'll come up with all sorts of approximations. The normal gradient descent essentially just says let's just move alpha in the direction. Okay, so one thing that helps me, and it might help you too, if you aren't already particularly well versed in the multivariable function optimization, is to think of most optimization algorithms as trying to do Newton-Raphson for multivariables, but it's just too costly. So if whenever somebody says there's a slightly better version, it's just, they found yet another way of not computing Hessian but still getting all the good properties of Newton-Raphson. Okay.
But f double dash x doesn't has the direction of the movement as well. If we just replace it by a factor alpha, or is it only in the minus? The direction.
No. So I'm not giving you the actual details of two-dimensional Newton-Raphson. I'm just trying to tell you that if you want to understand, you should really just be using this everywhere. And there should be just one machine learning algorithm, one function optimization algorithm. There are many, because doing this for multidimensional functions is costly. Yes.
Won't the Hessian matrix be sparse?
How does it matter?
The computation can be done efficiently in linear time if it is sparse.
No. So if you find a faster way of doing Newton-Raphson well, that'll be great. Okay, there are all sorts of structure that people try to use.
No, because when the number of variables will increase, the number of zeros in the matrix will also increase.
Why?
Because it's not necessary that in all coordinates the derivatives of all the functions have to be some fixed value. They will be necessarily zero.
Why should it be? Why is that obvious? Actually, there is something to be said for what he's saying. I don't know if you guys understood this. One of the points is our intuitions of higher dimensions are woefully inadequate. They're mostly wrong. Okay, we think of one-dimensional functions and maybe see a couple of two-dimensional or three-dimensional functions and then say, oh, I know everything about multi-dimensional functions. And one of the interesting issues in all these cases is that, okay, by the way, so you guys notice that Newton-Raphson has its problems. It's a local method, right? And so, for example, I can, tell me where Newton-Raphson can go bad. This is a nicely well-behaved function where the local gradient essentially is telling you how the function is behaving in a large interval. Okay, but the function can continue to be continuous and still go up and down all over the place. So, for example, if I had, if I had some function, let's say, which is actually, let's see, so, yeah, like that, something like that. Okay, so then depending on the x you pick, so for example, if I pick the x here, okay, then it tells me to come here. Did you see what I'm saying? So basically, depending on where you pick the x, you might actually go away from the zero.
So this is a question that I had, because a zero is not only a maximum, it's also a minimum.
Yes.
So how do you know that you're not approaching a minimum instead of approaching?
No, again, all I'm saying is, if you swap in all those issues, you're in the right shape. Okay. For any of the algorithms you're using, somebody has actually had to prove once that basically there would not be that the function the only zeros you will get would be maximums. Okay. For many scenarios like the one that we just saw, that is true. Okay, a bigger issue is, there's not only don't you know whether you are a maximum or a minimum just by looking at the partial derivatives, you also don't know whether you are the global maximum or one of the local maximums, which is what winds up being a huge issue. Okay, the second one, nobody knows how to solve. That means finding global maximum, there is no way of ensuring that you found global maximum. Do you guys remember how you found global maximum in calculus? If I give you an interval, I give you a function and I give you an interval and say find the global maximum, what do?
We calculate f dash x and then put in all the values in.
So you find every one of the local maximas and minimas and line them up, sort them and see which one is the biggest and say, oh, that must be the global maximum in the interval. In fact, you also throw in the value of the function at the interval itself. Even if you wind up having a scenario where the function goes in the interval that you have, the function goes like that, and then I'm taking this interval, right? In this interval, this looks like a nice maximum, but within the interval, the function is higher here and here. That's why you wind up also taking the values of the two edges, okay, two final points. But the bigger issue is you're enumerating now. You're not just finding, the gradient descent method is not guaranteed to take you to anything other than the local minimum. Similarly, a gradient ascent method is not guaranteed to take you to anything other than a local maximum. In those fortuitous cases where they wound up getting the global maximum or minimum, it wasn't because they are smart. It's because the function happens to have only a global maximum or a global minimum. That is why, you heard the word convex functions, right? Why do people like convex functions? Convex function looks like this. It only has one minimum. Concave function looks like the opposite of it. It only has one maximum, right? So if you throw in somebody, who can make a beeline to a minimum, and it turns out a minimum also is the minimum, then you can, say we win. You see what I'm saying? So it turns out that actually you can show. Where am I? Okay. You can show that this function is concave. And once you can show that the function is concave, that answers your question. That the only thing that you can have is a maximum. And there will only be one maximum. So you find a maximum, you're done. What?
It's the convex that gives you the.
No, convex is like this. Concave is like this. Okay? This is neat stuff. Actually, we are going into more details. For those of you who didn't actually see the lectures, this is all, unnecessary second order, But if you saw the lectures and you had questions like this, these are important questions. The reason you don't have to worry here is because you can actually show that this function is concave. Now, I also mentioned, by the way, that for the complete data, this is a Bayes network with complete data. If you take Markov network with complete data, you will get an uglier function. That uglier function does not have the beautiful properties that when you take the partial derivatives, they nicely get unentangled. That means each partial derivative would be about just one variable. And you just solve that, you will get that value. They're not simultaneous. You see what I'm saying? Okay, that is true here. It turns out for Markov networks with complete data, if you write the maximum likelihood expression, that does not have this property because, as I told you, Markov networks will wind up having a normalization constant. And I just mentioned it, but we didn't go into details. Which the normalization constant brings in all the variables together. Because of which this property doesn't hold. So you actually have to do gradient ascent. Okay, the thing that you're missing, the thing that the Bayes network based, the maximum likelihood estimation based learning for Bayes network is so simple. It's so simple that if you think this is learning, then you think, oh, learning must be extremely easy. I don't know why people write big books, right? Basically, this is just, take ratios of the counts and you're done. Okay, but you're only lucky this once, it turns out. Okay, from here on, things become hard. Okay, they can become hard in two different ways, as I mentioned. One, of course, is the partial derivatives don't have to be unentangled. And the second is the partial derivatives, here you notice that not only are the partial derivatives unentangled, they are also essentially linear equations, so you can find the roots. You're saying, partial derivative with respect to x is equal to 0, you can find the value of x directly. If this were a entangled nonlinear equation, how are you going to find zeros? You go back to Newton-Raphson, or you actually do the gradient ascent. Now in that case too, how do you know that when you do the gradient ascent, you will actually reach maximum and not minimum? Because it turns out the expression, that maximum likelihood expression, can be shown to be concave. Okay? And once you show that to be concave, then you know that the only thing anybody can find where partial derivatives become equal to 0 must be a maximum. And it must be the only maximum. You see what I'm saying? Okay, so complete data Markov networks is harder than complete database networks, and yet they're still simpler because the one thing that you find would still be global maximum. Then comes the incomplete data scenarios. Incomplete data, even with Bayes networks. If I have my thing here, incomplete data Bayes networks, the maximum likelihood can essentially be an arbitrary function. That means it can have local minimas and maximas. This is just a function. The maximum likelihood might look like this. Okay, so in this case, actually, it matters whether you find the global maximum or not. In fact, in EM is not guaranteed to find the global maximum of this function. It's only guaranteed to find the local maximum of this function. Okay, so this is another thing to keep in mind. Gradient ascent is a local search. Ascent, comma, descent, either of them, you can use it in which way. It is a local search method. Okay, it will only find local maxima, local minima, local saddle points. Right. In fact, once you get out of, in fact, remember the saddle points, by the way? People remember saddle points? The x cube function. This place, that place, the gradient would be 0. It's neither maximum nor minimum. It's a saddle point. Okay. So you actually had to worry about all of this, just like Mark was worried about. It just so happened that for the cases, for certain cases, you don't have to worry. For complete, so whenever your objective function is convex or concave, you jump up and down and celebrate. Why? Because you know for sure that gradient ascent method or descent method will find the global maximum. Now, if you're stuck with something like this, what will you do to find the global maximum? You start from a place, basically look for the nearest maximum. Remember that if you have more time, start from another place and find another maximum. And see if that maximum is bigger than this maximum. If so, this is my maximum. You see what I'm saying? And unless you know the function, you don't know where else to start from so that you'll find the better maximum. Okay, so the local search methods working on functions which have both many maximums will basically have to iteratively improve their estimation of the maximum if they have extra time. Most people just find the closest maximum and say that's enough.
So how about using heuristics to find a good initial starting point?
You can. You just need to give me good heuristics for n-dimensional functions, n-dimensional continuous functions. And that's basically what people try to do. I mean, it's good to at least get a handle on, why do these algorithms differ? Okay? And then, since as long as I have this here, I want to also point out that one of the nice things about EM, actually, I don't know if you understood the discussion on this. One of the nice things about EM is, so gradient descent, gradient ascent is the only thing we care about right now. We're trying to find the local maximum right now. Okay. Now, to get the gradient ascent, all you need to do is compute the partial derivatives and make a step in the right direction. A small step in that right direction. Okay. Now, the question is, what should be the size of the step? And one big issue, actually, in fact, is what Newton-Raphson would say is that the size of the step should sort of be sort of driven by the second derivative. But we just said that the second derivatives for n-dimensional functions are too hard to compute. At least people try not to do it. Okay, and so what you'll wind up doing is, so there is no real reason to have a single step size. People tend to start with a big step size and then slow down. As the gradient is becoming closer to 0, they try to make smaller steps. Okay, now, of course, that's not foolproof. In fact, where gradient being close to 0 and still you should make big steps will happen? Think of a function which is flat in some large region, right? So the gradient is close to 0. Basically, it's close to 0 there. And yet, the maximum is somewhere up there. So it's like you are in Deccan Plateau in India and are thinking, let me make small steps, lest I forget, I overstep Everest. Everest is out there somewhere, and you're making small steps because your derivative is small. Right? Okay. So what you would like to do is essentially make adaptive sized steps. This is a huge deal in multi-dimensional function optimization. How do you compute the step size? Okay, and EM can be understood very nicely as essentially doing gradient ascent, except the step size is determined in this indirect fashion. Okay, so what this picture is essentially trying to show you is what EM tried to do is, this is some function, some unknown function. If you have it in front of you, of course, you can see this is the maximum. Okay, you have some unknown function. Okay, and then you essentially found a lower bound for this unknown function. The lower bound has the property that at this current point, the lower bound is equal to the function value. And yet it is a lower bound. Now furthermore, this lower bound function should be tractable. When people in calculus say tractable, what do they mean? It should be easy to compute partial derivatives and equate them to 0. Really, that's it. Okay, this is a bad function because it turns out finding partial derivatives and computing them, equating to 0, winds up being quite costly. Okay, so this one will wind up being a tractable function similar to, because this will be a tractable function. This is, by the way, this is a concave function, right? And what happens, when do you get a concave function? If you have complete data in the network, if you converted your problem into a complete data learning problem, then you will you're guaranteed to get a convex function, a concave function. What did EM do? It started with missing data, but just went ahead and converted into complete data by just filling the blanks with whatever its guesses are. Right? And once it converted into complete data, then it basically got this expression. This would be the maximum likelihood function. Now this maximum likelihood function, this would be the likelihood function. this likelihood function has the property that it's going to be a lower bound on the true likelihood function. Okay, and so if I were to compute the maximum for the lower bound, since this is still a lower bound, that means if I can go up to this point, I know that the function still has to be above me. So I am guaranteed to be still before them, basically I'm still guaranteed to make the right movement if I just take the x corresponding to this and take the f value there. Okay, so instead of just making a small step on the function, I made like a big step from here to here. Okay, and that is basically what EM is best understood as. Okay, and then the way these lower bounds can be shown is also very cute. Actually, it's based on the Jensen's inequality, and Jensen's inequality essentially is sort of saying that in a convex function, and opposite is true for the concave function, in a convex function, this is, let's say you have x1 here, x2 here. Then every point on this line can be written as t times x1 plus 1 minus t times x2. Oh, what did I do? Okay, right? That's basically where t is a number between 0 and 1. It's a, right? I mean, you'd normally write it as alpha times x1 plus 1 minus alpha times x2. Okay, right? And then this is the function itself. So this is f of this whole thing. Right? T times x1 plus. So all we are basically saying, sorry, I didn't write it correctly. See, I think it's easier to write it here. So this is x1, this is x2. There is a secant there, okay, and every point here can be written as alpha times x1 plus 1 minus alpha times x2 for some alpha between 0 and 1, right? If alpha equal to 1, then it's just x1. If alpha equal to 0, then it's just x2, and every other point is in between this. Now, for this point, the function, this is the function f. The function's value itself is f of alpha x1 plus 1 minus alpha x2, right? And then these, and then at this same point, the average for these two would essentially be x1, sorry, so the
Alpha times alpha by x1 plus 1 minus alpha.
Yeah, alpha times x1 plus 1 minus alpha times x2. That's basically what it would be here. So the value here would actually be alpha times x1 plus 1 minus alpha.
F of x.
Oh yeah, sorry. F of alpha times x1 plus f of 1 minus, no. So these are weighted average of the function values at the points, and this is the function's value on the average itself. And convex functions have the property that this value will always be lower than this. And concave would be the opposite. And this is basically what Jensen's inequality says. Now, one of the interesting things is you're thinking of this right now in terms of one dimension. So you just think of one alpha. Okay, if you have a multi-dimensional point, okay, then you are essentially going to get the convex combination, you need to essentially get an alpha vector. Okay, this vector would have numbers between 0 and 1 such that they all add up to 1. The positive numbers between 0 and 1 and such that they all add up to 1. Such a vector can also be called a what?
A unit vector?
No, no, it's not a unit vector actually. It is a probability distribution, right? It's a probability distribution. So in fact, even though Jensen's inequality is about convexity, it turns out that the way you combine, the way you get convex combination over any n-dimensional space is basically having this weight vector. That weight vector such that all the weights are positive and they add up to 1. And so you can say that is just a probability distribution. Okay, and so what actually this can be seen as, if you put your probability hat on, then this can be seen as expected value. Suppose this is the average, in this region. This is the expected value of f of x. And this can be seen as f of expected value of x. And so Jensen's inequality can also be seen as establishing a relation between expected value of a function and the expected value of the variable itself. And that's what is being done here to get the lower bound characterization. And essentially that in the EM, the expectation maximization step, you're making a bunch of these kinds of iterations until you find a local maximum. Other questions? So one thing I hope you remember is for simple cases, the likelihood itself is basically concave. And so gradient descent is guaranteed to give you the optimal solutions. Because the next thing, so you did hear the Bayes learning perspective on this whole thing, right? So what's the point about Bayes learning versus maximum likelihood learning? What's the major difference? Yeah.
Because maximum likelihood only provides one answer, while Bayes provides a possibility of all of them.
So actually, that's an interesting question. What is the goal of learning? What is the goal of learning? How do you judge a learner? In terms of prediction. Does Bayes learning and maximum likelihood estimation learning differ in that aspect? They both make a prediction. And you can compare apples to apples. All you are essentially saying, and what you're saying is right, what you're saying is Bayes learner never actually made a commitment to a single hypothesis. It is in essence holding a posterior on all the hypotheses and are using a weighted summation of what the hypothesis, each hypothesis says, okay, this hypothesis says the next one is going to be a cherry, and this one says the next one is going to be a line, this one says the next one is going to be a cherry, this one says the next one is going to be a line, and each of these hypotheses, I have a distribution over them. That means I have an actual probability distribution. So if these hypotheses are discrete, then I have a vector, a weight vector which adds up to 1. So then I would do a weighted prediction. That's what Bayes network would do. MLE just goes with one hypothesis and says whatever that hypothesis says, that's what I'll say is the answer. Okay, right? So Bayes learner never actually. So one interesting way of thinking about it is there any learning in Bayes learning?
There is no inference.
What?
There
There
is
is what?
There is no inference done.
So I think technically the most important point I hope would make a humongous sense by the time this set of lectures are over for you is there is no difference between learning and inference as far as Bayesians are concerned. There is no difference. There is no such thing as learning. Okay, because in essence, the base learning part that we looked at, and actually we can go back to that a little. Base learner never, it basically keeps track of the hypothesis as an extra variable, as an extra random variable. Okay. Yeah. So, just going over this once more, basically, this example is a nice example to motivate base learning and the distinction between it and maximum likelihood estimation and map estimation. But there is something, what this particular example hides is the fact that here your hypotheses are only 5 hypotheses. Somebody told you there are only 5 possibilities. You just have to learn which of them is the possibility. Okay, now after this, actually, I talked about MLE, right? Now, when I went to MLE, I used examples like this. Yeah, I wrote an example like this. How many hypotheses are there? How many hypotheses are there?
They are infinite.
Infinite number of hypotheses. Right? Because for every different value of theta, theta 1 and theta 2, there is a separate hypothesis. It looked like fine and dandy that in the candy example, you did not make up your mind as to which of the 5 hypotheses is the correct one. You pulled them all along as the evidence got presented. By doing that, you didn't have to differentiate between learning and inference. Okay, which is a beautiful thing to do. But I also want you to understand that to do that, a technical problem that you have to, challenge you have to deal with is if your number of hypotheses are infinite, exactly how are you going to pull that? Okay, which is why once we start talking about Bayes networks, Bayesian learning next class formally, we will start talking about things like distributions over distributions. Right? Theta is a distribution. And you need to talk about, don't look sad, okay? It's all simple. You need to talk about distributions over distributions. And all that means essentially is think about this. Think about, I wish I could show this. So actually, in fact, for a 2-dimensional case, this is the idea, right? So suppose I just have a single parameter theta. Single parameter theta. Okay, so the distribution it is giving me is theta and 1 minus theta. That's the distribution. Okay, so as I vary theta between 0 and 1, I get a different distribution. The question is, do you happen to have a prior on the hypothesis? In the candy example, you had prior on the hypothesis, right? Did you have prior on the hypothesis in the candy example? Yes or no? Who told you? Where is the prior on the hypothesis? This is the example. Where is the prior on the hypothesis?
Distribution type.
There, this one. This one. How did you know this? Did you know this over and above the data, or you just did this come from the data itself? Ask yourself the following question. So, from a learning point of view, the data is the next candy that you see, right? So that's just data, and you're learning from the data. This information is the prior on the hypothesis. You're using this. Is this part of the data? So somebody gave you this information separately. The reason I make such a big deal about this is statisticians, the classical statistics does not believe at all in Bayesian way of doing learning. In fact, they don't believe in Bayesian statistics. So, to the extent there are holy wars in academia, okay, we have our own little holy wars, Linux versus, Windows versus something else. In the statistics departments, the holy wars are between Bayesian versus frequentist statistics. Okay, Bayesians basically don't think that you should be talking about hypothesis as a random variable. And if it's not a random variable, how dare you tell me the distribution over it? See what I'm saying? Okay. We won't get involved in the religious wars. They're still going on, but mostly Bayesian's won. At least that's what I would say, because most of the working machine learning systems are Bayesian approach, use Bayesian approaches. Okay, but the interesting thing is this is extra knowledge about the data, and part of understanding the statistics people's reluctance about extra knowledge is, it turns out the language matters. If I told you this is extra knowledge, background knowledge, it looks good. If I told you this is your bias, it looks bad. You're prejudiced. Okay, you're prejudiced into looking for this kind of, all you really see is this. And anything else, according to statistics people, is, you're going out of the data, you shouldn't really, you shouldn't go out of the data. And one of the interesting things is the Bayesian learning and the frequentist learning would basically say the same thing for large data kits. That means if you see enough data points, you would pretty much know what the hypothesis percentages are. See what I'm saying? Okay. What is interesting really is what do you do if you have only a few data points? Okay, here's my question. I took a coin. I tossed it. Heads it came. Next it came tails. I want you to tell me this coin basically, I'm talking about the fairness of this coin. So fairness of the coin basically is theta h, which is the probability with which it comes heads. The coin that I picked up from my pocket, you don't know what its actual, probability of coming heads is. I just showed you, I tossed it twice and I showed you heads and tails. What's your probability, what's your estimate for theta h? You need to do this, right? MLE can tell you how to do this. It's a 0.5. Okay, so next, I picked a different coin. It came heads. What do you say? You have to tell me right away. This is the data, and you have to tell me, okay? You say, well, as far as I'm concerned, Rao has one of those magical coins. Theta h equal to 1.0. Now you may not like this. Suppose you have something else like this, h, t, h, h. You see what I'm saying? Okay. So then you will basically say, well, this one, according to the MLE, this would be theta h would be 3 by 4, and so theta t would be 1 minus 3 by 4. Okay. Now, clearly, you basically, okay, so the other interesting question is, you were laughing when I showed you this, right? I didn't ask you to laugh, you laughed. Okay. So presumably, it did not gel well with your intuition. Now, what is your intuition? Do you really care about theta h? What you care about is the prediction. So I had this same coin, okay? I just tossed heads. I'm about to toss. Tell me, is it going to come heads or tails? Right? So if you believe 1.0, you will say heads. If you believe, if you on the other hand believe theta equal to 0.5, then you have your own little coin, you toss it and say whatever it comes. It turns out, by the way, that's like the best way to guess the other guy's coin toss, if it's a fair coin. Okay? Right? So in this case, in one case, even though the data MLE was telling you theta h is 1.0, you didn't believe it. You didn't believe it because you actually had a prior on theta. So when I picked up a coin from my pocket, it is some random coin, and so it will have a heads probability, theta h, that would be between 0 and 1. heads probability that's between 0 and 1. The real question is, what is the distribution over theta h? So I did not even actually toss my coin. I just picked up my coin. Okay. So what did you think if somebody just picks up a random coin? What is your general intuition as to, before you even saw the data, what is your general intuition as to what's the more likely value of theta h? So for example, I can say that prior knowledge, and that goes back to the guy who was rolling his eyes because he was worried about distributions over distributions. Okay, but it turns out in this case I can write you a distribution over distributions. Okay, so you're trying to figure out how theta h looks, right? So suppose you thought it's like this. Your prior is like this. I mean, who the heck knows Rao? He can have one coin each of possibly for the infinite possible values of theta h. He has one coin which gives that theta h as the heads thing. That means you really have no idea. Anything is possible, right? If on the other hand you put something like this, then that means Rao seems like a reasonable guy. Reasonable guys carry reasonable coins. Reasonable coins tend to have 0.5 as their probability of coming heads. Maybe there could be manufacturing defects, etc., so they might throw them off a little bit, but it's not likely to be very high probability at the edges. Right? So if you used a uniform prior distribution over the hypothesis, that is like saying anything can happen. If I used a unimodel prior distribution that peaks at 0.5, then I'm saying that 0.5 is more likely. What if I did something like this? That's a distribution too. Now, anybody worried about the fact that I only need two numbers for a coin, heads probability, tails probability, and yet this distribution is giving infinite number of values? Each of these distributions are giving infinite number of values. I'm intentionally confusing you. If you're not confused, it's good. Because we are talking about the value of theta h. Once you give me the theta h, 1 minus theta h is theta t. Right? But the value of theta h itself can be between 0 and 1. Every possible real number between 0 and 1 is a value of theta h. So to talk about your knowledge, your prior knowledge about theta h, you need to talk about the distribution over this real valued variable. You see what I'm saying? Okay, so look, so I can have a distribution like this, I can have a distribution like this, I can have a distribution like this. Now, that basically this way you think Rao is kind of more likely to be carrying a heads biased coin. Furthermore, I can have a distribution like this. So the difference between this and this is, according to this, you think both of these think that the more likely value for theta h equal to 0.5, but the blue one thinks the variance is much lower. The red one thinks variance can be quite high. Notice how many things I'm able to say about my prior knowledge about some random guy's coin, just using probability distributions. Right? Okay, now I can also do the following thing. What if I want to say this? That means Rao either has a 2 heads or a 2 tails coin, mostly. Right? Okay, now these are all the prior distributions over the theta variable. The prior distribution for the discrete variables were nice simple things like 0.25, 0.25, 0.5, whatever, those numbers add. Okay, that was a distribution. Okay, sorry, these are the numbers. Okay, 10%, 0.1, 0.2, 0.4, 0.2, 0.1. That's the distribution for you. There are infinite of those distributions too. But I told you this is what is actually my belief as to what is the likelihood of these hypotheses. Okay, here for the single continuous variable that is just deciding my single hypothesis, I needed to write this. So the thing I want you to actually see is this. Imagine I were to give you a single distribution. Imagine I were to give you a single distribution which has some parameters alpha and beta. And playing with alpha and beta, I can get a uniform, this one, this one, this one, or this one. Would you be happy? Because I made this big thing about, these are kinds of background knowledge I can have. Turns out, does anybody know what that distribution is? What? What? No. I wish I can show this. I can show you in a minute. It's a beta distribution. Okay? Let me show you. Give me a second because it's worth doing this, because next time we can start with less magic. Yeah. Do I have it here? No, it's not in this, I think. It's another one. Oh, I don't have it. Oh, there you go. Sorry. Let me just. If I can get you to the right slide. Okay, this is called a beta distribution. Okay, and the beta distribution basically is some normalizing constant times x power alpha minus 1 times 1 minus x power beta minus 1. Now the parameters that you care about are alpha and beta. By playing with the alpha and beta, you can get beta distribution to look like this, or like that, or like that, or even like the cup. What? You can also you can get very close to uniform. Okay. Now, this is a distribution that I could draw on the board, because I only had single variable over which I am distributing. I need the proper distribution. What you would wind up needing to actually talk about theta, theta 1, theta 2, which is what we had there, especially if theta, theta 1, theta 2 tend to be correlated, is you need a probability distribution over 3-dimensional vector. So you need a beta distribution generalized to n dimensions. Beta distribution that is generalized to n dimensions is a Dirichlet distribution. Okay, so that is the Dirichlet in the latent Dirichlet allocation. Okay, now the magic reduction part is that, look, before you saw the first data point, you had some knowledge about what's likely to be the value of the theta edge. Okay, if you are doing statistical learning, that knowledge has to be representable as some distribution over the hypothesis. Okay, it turns out that beta distribution has certain nice mathematical properties such that it does have a reasonable amount of expressiveness about showing both bell-shaped curves and inverted bell-shaped curves, as well as close to uniform distribution. And it has it has very nice properties in terms of you can interpret this alpha and beta. It turns out to be equivalent to, in terms of, let's say, coin toss example. If before you saw, actually somebody said this, where did the hypothesis come from? And somebody said from the previous experience. And what is the previous experience? In your life, you have seen lots of coins be tossed. And you counted, supposedly you had no other work than to remember how many times the heads came and how many times the tails came. So of all the coins you have ever seen in your life, alpha of them came heads. beta of them came tails. Then it turns out that, basically Dirichlet distribution, that the alpha and beta in Dirichlet distribution essentially take that place. That they're kind of telling you how many times you saw heads versus tails. And that also will bring, again, we'll go through this again next class. This also will tell you how to deal with MLE, which has this annoying property of seeing the first two heads and say it'll always be heads for now onwards. Okay? And convert that. And basically do that by saying, well, imagine that before you see this, I have seen already alpha heads and beta tails. Act as if I've seen virtually alpha heads and beta tails. Okay? Then the heads probability would be h plus alpha by, so heads probability would be 2h, 2 plus alpha by alpha plus beta. Plus 2. Okay? And the tails probability can be computed the same way. The nice thing is, as the data increases to infinitely long, eventually these numbers wind up dominating alpha and beta. And so the virtual samples you imagine doesn't matter. I want you to think about the fact that this is essentially the difference between learning and prejudice. It's completely out of the curriculum, but that's the difference between learning and prejudice. Okay? There is a great argument to be made that if you say, I don't know, if you see somebody on the road, if you say, I don't know anything about what they're going to do to me, that's not a particularly efficient way of living. Because you actually know what happens. If you saw like a bus coming towards you and you're in the middle of the road, you say, I don't know what's going to happen. Because some buses stop, some seem to run over. This one can be either one of them. You see what I'm saying? You do actually use your prior knowledge to make decisions. Now, if after seeing your prior knowledge being completely defeated like 10 million times, if you still stick to your prior knowledge, then I say essentially you have strong biases and prejudices. How much our data I can show you, you're never going to change. Okay, now the idea is the word bias looks like a negative thing, the word prior knowledge looks like a positive thing. Whoever doesn't want to use prior knowledge, it's like saying, I just was born today. I'm just going to act as if the world is started today. And anyway, so we'll come back next class and look at Bayesian learning for one variable case and talk about generalizing it to multivariable case.